Okay, today we're going to talk about Newton's second law, and we're going to start by differentiating between kinematics and dynamics. So we spent a long time on kinematics, and kinematics is the study of motion. We are basically looking at an object's position. We're describing the motion by talking about its position, its velocity, and its acceleration. Okay, but we never really explain in kinematics why does something accelerate. So in dynamics, we're going to study why something accelerates, right? Why does something accelerate? What causes it to accelerate? Okay. And as part of this, we're going to look at Newton's three laws. We've already talked about a couple of them. We're going to talk about the second law today. So real quick, let's take a look and review Newton's first law. So Newton's first law says that an object remains at rest, or an object at rest remains at rest, or an object in motion remains in motion at a constant velocity in a straight line, unless acted upon by a net external force. And we've taken some time and we've defined all those terms, okay? Now, the implication here, and it's a pretty big deal, the implication here is that a net external force causes an object to experience a change in velocity. Well, we know what a change in velocity is. We studied that in our last unit. We know that a change in velocity is simply an acceleration. So that means a net external force causes an acceleration. Now that's a big deal, right? So now we know why something is accelerating, because there must be a net external force acting on the object. Now Newton's second law simply tells us the relationship between that force and the acceleration. And we're going to have to bring mass into the equation as well, all right? So Newton's second law says that the net force acting on an object, and we talked about net, that just means total, so the total force. So we have to look at the total force acting on an object. That equals the object's mass times its acceleration. So if we look at kind of just the same equation rewritten, we know that acceleration is given by the net force acting on the object divided by its mass. Said in another way, the acceleration is proportional to the net force. That means if the net force increases, the acceleration increases as well. Okay, we can be more specific. We can talk about if the net force doubles, the acceleration will double. And then we know that the acceleration is inversely proportional to the mass. That simply means that as the mass doubles, the acceleration doesn't double, it's cut in half. Okay? So let's go ahead, let's put a couple extra things in our notes. We'll talk about net force. I'm going to change the color here in my pen. We said that the net force is just the total of all the forces acting on the object. And we have to go one object at a time. Okay. We know that, and we talked a little bit about this with the first law, that forces acting in opposite directions will subtract. So basically what that means is that if I have two forces acting in the same direction, I know the total is the addition of those two forces. If I have two forces acting in opposite directions, for example, one to the right and one to the left, I know I'm going to have to subtract one of those forces from the other, okay? A couple other things to keep in mind, okay, that the net force can be zero even if there are forces acting on the object. So even if there are forces acting on the object, the net force could be zero. Okay. Just means that the forces all added up to zero. So for instance, you can take a look at something sitting on the table right now. Maybe you have a book sitting on your table. There are definitely forces acting on that book. They just happen to add up to zero, so the object is not accelerating. Last thing we want to know is that we're going to measure forces in newtons. And we talked about that when we talked about Newton's other laws as well. Okay. We've talked about mass before as well. Nothing has changed here. It's still the amount of stuff that makes up an object. And we're still going to measure mass in kilograms. This would be one good spot to remind us that there are 1,000 grams in 1 kilogram. Okay? All right, so let's take a look at a couple different situations here. And we're going to try and figure out the net force. So our whole goal when we are doing dynamics problems is often going to be figuring out what is the net force acting on the object. Because if we know the net force, then we can find the acceleration. And once we know the acceleration, we can predict the future. We can predict what is the object's position, what is its velocity in the future, right? So that's what our goal is, okay? So for each of these situations, we're going to find what is the net external force on the box, okay? We're going to assume that each person can push with a magnitude of 20 newtons, and we're going to assume, as we often do, that the positive direction is to the right, okay? So the first thing we want to do is we want to draw the forces acting on the box as arrows, starting from the box's center. So if I have one person, this picture on the left right here, if I have one person pushing to the right, that means I'm going to have one force acting on this object. These lines don't straighten out very well. I'll try and draw a straight line, okay? Right now, I'm only looking at the applied force. I'm not going to talk about some other forces that I know are acting on this box, specifically gravitational force and the normal force. I'm just going to worry right now about the applied force, okay? Now, the net force that I know must be acting on this box must be 20 newtons, because I know that that person is pushing with a force of 20 newtons, okay? Let's take a look at the middle box. In the middle box, I've got one person pushing to the right with 20 newtons. And I've got another person pushing to the left with 20 newtons. Well, in that case, the net force is going to be 0, because those two forces are going to cancel each other out. And then in our last situation here, I've got somebody pushing to the left with 20 newtons. And it's standard for these pictures that we're drawing, and we're going to name these in a little bit. They're basically called free body diagrams. But it's standard in these pictures, these free body diagrams, that we draw the force as an arrow pointing away from the object. So even though the person is standing on the right side of the box, we're going to draw this arrow, since they're pushing to the left, we're going to draw this arrow going away from the box. I would not draw it, and it's really just a convention, but I wouldn't draw it like that. Okay, that's not how I would draw that, okay? So in this case, I know my net force is going to be negative 20 newtons, because the force is to the left, and we said that right is positive, and therefore left is negative. So let's go ahead and talk about some of the forces that we're going to see and we're going to have to identify as we move on and learn how to draw free body diagrams. A very common type of force is the applied force. So you can use F applied. A lot of times I'll just put F sub A as well. I usually use capital A. And the applied force is really any force that we see, maybe like a person applying, okay? It can really be applied by anything, but we're often going to see it applied by a person. Okay. There won't always be an applied force, but sometimes there will be, all right? We're going to talk about the force of gravity, and we've already talked a little bit about the force of gravity, and we're going to use F sub G to stand for the force of gravity. It's simply a force of attraction, and I'm going to change this definition up later in the unit, but it's the force of attraction. And it's always attraction, just like we talked about in the last unit, how the Earth is always attracting objects. It's never repelling them. Force of attraction between the Earth and every other object on the Earth that has mass. So really objects with mass. Okay. Now, we're going to talk later on, and we're going to kind of expand this definition. But for right now, let's stick with that. Now, if you were on, say, another planet, it would be the force of attraction between, say, Jupiter and you or whatever was on that planet. Okay. For now, we're going to stick to, for objects located close to the Earth. Okay. And we know that it always acts down, because we know that that is always an attracting force. We can always determine the force due to gravity because we know it's a very simple equation, and we're going to, if we haven't talked about it yet, we're going to talk about it now. The force of gravity is equal to mass of an object times g. So think back to your weight versus mass lab. This is exactly what you saw in the force for weight versus mass. So highlight that. We're going to make sure we keep that in mind as we move forward, okay? All right, let's talk about another force, one that you're probably pretty familiar with. This is the force of friction. Okay, this force occurs when two surfaces are in contact. Okay, we're going to study this force quite a bit, but a couple things to keep in mind is that this force always acts parallel to the surface. Okay, to the contact surface. And it's always going to oppose a slipping. So it's a force that resists slipping or sliding. And depending on what book you read, sometimes you'll see that it opposes motion. That's actually not true. Okay, it doesn't resist motion, but it does resist slipping and sliding. So, and we have two types of friction. We can have static friction, okay, which is the friction that occurs when the object is not sliding. And we have kinetic friction when the object is sliding. And we'll get more into these as we go through our unit, okay? The next force we have is the normal force, okay? And this is a force that occurs when two surfaces are in contact, similar to friction. But as different than friction, this force is perpendicular to the surface. So we can use our little perpendicular sign. That's not a very good one. Perpendicular sign from math class. Perpendicular to the surface. Okay. So for instance, an example of the normal force would be if you have a book sitting on a table, we know the force of gravity is pulling down on the book. Something must be pushing up on the book or the book would be going down. And what that is the table pushing up on the book, and we call that a normal force when the table is pushing up on the book. Now, Newton's third law tells us that the book is also applying a normal force to the table. It's just going down, okay? So we're going to use the normal force, and we're going to find that that's a very common force to have in our free body diagrams as well, okay? Another common force is going to be the tension force. We're going to see that a tension force is just a force associated with something that's pulling usually. So something like a string or a rope or a chain, okay, a lanyard, anything that's associated with a pull force. You won't see a rope pushing. Okay, so tension force is not going to be a pushing force. And we're going to find that the tension force is constant along the length. It doesn't change, okay, so it's constant along the length of the rope or whatever it is, okay? And it's always in the same direction as the rope. So that's kind of what we need to remember about our tension force. And then the last force that we're going to talk about right now is air resistance. There are, of course, other forces, but these are the main ones that we're going to talk about. Air resistance. Air resistance is similar to friction. Okay, it occurs when something is touching the air. Okay, and that's what occurs when something is moving through the air. Okay, and it'll get larger as velocity increases. So for the most part, we will ignore this unless told otherwise. For right now, most of the problems we're going to ignore air resistance. But then we're going to talk about skydivers, and in that case, we will not be able to ignore air resistance. But we're not going to worry about that right now. That's getting a little cart before the horse, okay? So let's talk about our free body diagram, okay? When we're determining the net force on an object, it's really crucial to visualize and understand all the forces involved. So a free body diagram allows us to do this. So we're going to do a lot of free body diagrams over the next couple of days. And when we write, a lot of times we call them FBDs just because, physics teachers, we like to take shortcuts. Okay, so here's how we're going to do our free body diagrams. The first thing we're going to realize is that it's a drawing, but you don't have to be good at drawing. I'm a terrible artist, so you don't have to be good, because we're going to represent every object, no matter how big, no matter how small, no matter how difficult to draw, as a dot. That's right, just a little dot. So if I can draw that, you can too. Okay. We're going to talk about, we're going to look at the forces, and we know they're going to act from the center of the object. And the size of the arrow is going to represent the force's magnitude, or the force's size. This word magnitude that you'll see and that I'll often use simply just means size. Okay. And only forces acting directly on the object are included. So what's very confusing many times, especially since we've just finished talking about Newton's third law, is that people like to put the third law force pairs acting on the one object. Well, we know that's not the true, because we know with third law force pairs, there are two objects, right? I'm pushing down on the book is pushing up on me. Only one of those forces can appear on the free body diagram of the book, and it's the force that I'm applying to the book, not the force that the book is applying to me, okay? So we have to be careful with that. We want to make sure we get our free body diagrams situated, all right? So let's take a quick look at a couple of simple free body diagrams. And the first one says an apple sitting on a table, and there's no acceleration. So I'm going to draw the little dot. And the first thing I'm going to ask myself is, okay, what forces are acting on there? And specifically, I'm going to look at what are the non-contact forces. Remember, there are only three types of non-contact forces. There's gravity, there's the electrical force, and there's the magnetic force. We're not ever going to worry about the electrical and magnetic force, not until much, much later, probably towards the end, if ever, of second semester, okay? So the only force I have to worry about is force of gravity. And I know the force of gravity is always going to be acting on every object. And so I'm going to go ahead and I'm going to draw in a straight line down, because I know the force of gravity always pulls down. And I'm going to label it like that. Now you could also, because we know the force of gravity is always equal to mg, you could also just label this as mg. Right? It's the object's mass times g. So that's the only non-contact force. Now I have to ask myself, okay, well, what is the apple in contact with? What is it touching? Well, it's sitting on a table, so it's touching the table. Well, what kind of a force could the table be applying? It's applying a normal force for certain, and I know it's pushing up, so I can go ahead and put the normal force on there. Now, the other question you have to ask yourself is the normal force bigger, smaller, or the same size as the force of gravity? Well, in this case, since I'm told that there's no acceleration, that means that the acceleration has to equal 0. Well, if that's the case, then the net force has to equal 0 as well, and any forces acting on the object must cancel out. So the normal force has to be equal in size to the force of gravity, but it has to be opposite in direction in order for that cancellation to occur. All right, now let's look at a different situation. Let's look at an apple falling from a tree. In this case, I know there will be acceleration. The acceleration will not be equal to 0. So the net force will not be equal to 0. So here's the apple again. I always know I have the force of gravity acting on it. And now I have to ask, well, what other force is acting on the apple? What other object is touching it? Well, there's no other object touching it, so there's no normal force. There's no tension force. Some people like to put an air resistance force in here, but I've said that we're going to ignore that unless told otherwise, and we were not told to include it. So I'm not going to put an air resistance force. That means that that's it, right? Which makes sense, because now I know that by looking at this that the net force is not 0. So yes, absolutely, this object is accelerating. This apple is accelerating down. All right, let's try another one. A person pushes a box on a frictionless floor, and there is acceleration. So let's go ahead and draw our object here, just a dot. Same rules apply. I'm going to ask myself, what is the non-contact force? Well, of course, I've got the force of gravity acting down. And the box is sitting on a frictionless floor. The problem doesn't say anything about the object jumping up or down. So I'm going to assume that when it's accelerating along the surface of the floor. So that means that I must have a normal force that's keeping the object from falling through the floor or jumping off the floor, so that the normal force is the same size as the force of gravity. If the person is pushing the box, I know there must be applied force. Now, they don't say if they're pushing it to the right or to the left, so I'm just going to assume it's to the right to make things easier. and I'm going to call that the applied force. That's it. There's nothing else touching the box. I'm not going to include air resistance, and I know it's a frictionless floor. So that's the only forces that I have acting on this object. Now let's take a look at this next one. Two people on the same side of a table pushing it on rough carpet at a constant velocity. Well, this constant velocity is a key. This constant velocity is telling me that the acceleration on this object is 0, so the net force must be 0 as well. So right away, I'm going to go ahead and put the force of gravity. And I know that I'm going to have a normal force as well. That's going to be the same size as the force of gravity because I assume that the object is not jumping up or down. And then it says there's not just one, but there's two applied forces. So the way I draw this is I'm going to draw the first applied force. I'm going to call that FA1. And then I'm going to draw the second applied force. And I'm going to kind of draw it over here so that they're not on top of each other. They start in different places, but they are going in the same direction. Okay, so really, normally I would draw it like this and I would have that connecting there, but I wanted you to see that I was drawing a completely different line. All right. Now, this says that the object is not accelerating. Right now, if I left this free body diagram as it is, I would definitely have to have an object that was accelerating. So I know that there must be another force in the opposite direction. And that's going to be a friction force, okay? And I'm going to go ahead and draw that friction force like this. So that the friction force, when I look at it, the size of this friction force should be about the same size as these two applied forces when they're added up. Okay? All right, so far pretty straightforward. Let's take a look at a couple more. Okay, we've got a lamp hanging from the ceiling. No acceleration. So our acceleration is 0. So our net force is 0. So here's the lamp. And even though it's hanging from the ceiling, there's still a force of gravity. But since it's not going anywhere, the lamp is just hanging there, there must be another force in the opposite direction. We don't call this a normal force now because it's hanging from something. Maybe it's a rope or who knows what. We're going to call this a force of tension. But that's it. That's all there is. Okay, we don't have anything else. So we're done with that free body diagram. Let's take a look at our last one here. We've got a soccer ball being kicked. The ball is in contact with the foot and the ground. And there's some acceleration. So let's take a look. Here's our soccer ball. And we know there must be a force of gravity acting down. There must be a normal force going up as well. And I'm going to assume that the ball is only accelerating in the left-right direction. So I'm going to assume that the normal force and the gravity force must be the same size. If that's the case, the applied force, I'm going to draw it to the right just because it's easier. Right, so that's the applied force by the foot. So when I look at the soccer ball, I said, okay, there's a non-contact force and the force of gravity. There's the normal force, which is the contact force from the floor or the ground pushing up. And then there's the applied force from the person doing the kicking. Okay? That's it. That's how we do free body diagrams. So now let's try a couple of these. All right? So let's take a look at this is practice on your own, but hey, let's do it together. Why not, right? So let's look at a 10-kilogram box being pushed with an applied force of 25 newtons to the right on a frictionless surface. And we want to do three things here. We want to name all the forces acting on the box. We want to draw the free body diagram, and we want to solve for the acceleration of the box. This is new. This is why I want to do this problem together. So the forces that are acting on the box, let's see. I know the force of gravity has got to be one of them. Force of gravity is always acting. There must be an applied force because we're pushing with 25 newtons. There must be a normal force as well. So I'm going to go ahead and I'm going to draw that free body diagram. And when I do, it's going to look something like this. The force of gravity going down, the normal force going up, and I'm going to go ahead and draw the applied force to the right. Okay? This is the new part. Solve for the acceleration of the box. Gosh, how do we do that? Okay, here's our process. First part, you've already done. Draw the free body diagram. 100% of the time in a dynamics problem, you're going to draw a free body diagram. So if you're ever sitting there thinking, I don't know where to start, the answer is always the same. Draw a free body diagram. So that's step one. So I'm going to put step one here. Step two is always the same as well. It's going to be to write Newton's second law, which is F net equals ma. Write that down every single time. Free body diagram, then write F net equals ma. Step three is where it gets a little tougher. Step three is where we have to plug in what we know for net force and mass and acceleration and solve for what we don't know. Now, the reason we have gone ahead and we have done this free body diagram is because we want to plug in what we know into the net force. We're using our free body diagram to figure out what to put in for the left side of this equation. So looking at my free body diagram, I can see right away that the force of gravity and the normal force are going to cancel each other out, so they're not going to contribute to the net force. That means the only force that is contributing is the applied force. So the net force is going to be equal to just the applied force, and that's the left side of my equation. The right side of my equation now is simply still just the mass times the acceleration. Now I can start plugging in some numbers. The applied force, we were told, is 25 newtons. So 25 newtons has to equal the mass. They told me the mass is 10 kilograms times the acceleration. I can see, I do even a little mental math there. 25 divided by 10 is going to be 2.5. And my units for acceleration are always meters per second squared. So that's it. There is my acceleration. And now I could go ahead, and if I were asked to, I could do a kinematics problem that says, okay, well, where is this box located 3 seconds after we started pushing it, right? Because we would know its acceleration. We would know its initial velocity. We assume it's starting from rest, and we would know the time. So now we've got some kind of an extra step before we get to a kinematics problem. All right, here's another pretty typical problem. We're going to do this together, okay? So we've got two shopping carts, shopping cart A and shopping cart B, are being pushed by the same force. So we're going to assume that that force that's pushing is the net force, okay? We're going to assume there's nothing else going on there that would make them different. Okay, shopping cart A is twice the mass of shopping cart B, okay? Using Newton's second law in your explanation, compare the resulting acceleration of both carts. So let's think about what's going to happen here. We said that Newton's second law, F net, equals ma. And if we were to rearrange that, we would know acceleration is net force divided by mass. So we can see that the bigger the mass, the smaller the acceleration. So if each of the two carts, A and B, have the same net force, so the net force is the same for each of them, the cart with the bigger mass will have the smaller acceleration. So the bigger mass will have a smaller acceleration. So because shopping cart A, is twice the mass of shopping cart B, I would say that the acceleration for shopping cart B is going to be twice the acceleration for shopping cart A. Does that make sense? Hopefully, right? If I double the mass, I cut the acceleration in 1/2, so I know the acceleration for the heavy shopping cart is going to be 1/2 of the acceleration for the lighter shopping cart. So that's some proportional reasoning, okay? One more problem. You might like this one better because there's more math involved, okay? This time we have two physics teachers, and we're pushing on a 30-kilogram lab table across the classroom. We want the lab table to accelerate at 2 meters per second squared. We're giving it a mighty push. Okay, one teacher can push with 40 newtons. What force does the other teacher have to push with in order to get this table moving at 2 meters per second squared? This is a tough problem. So let's go ahead and do this together. Gosh, I don't know how to start. Hopefully you do, because it's the same as we always do. Free body diagram. All right, so here is the table. Now, we always start with our non-contact force, force of gravity going down. There must therefore also be a normal force going up because it's sitting on the classroom floor. And it says that we've got two teachers pushing. One teacher is pushing with 40 newtons. And the other teacher, we don't know what they're pushing with. So I'm just going to call this F applied. And I'll call it F applied 2. Okay. They told us to ignore friction. So that's it. Those are the only forces acting. Now, as we talked about before, we said that the normal force must be canceling out with the gravitational force. Okay. So now when I want to go ahead and I want to write my F net equals ma, right, because that's always my second step. First step, free body diagram. Second step, write F net equals ma. I can see that my net force is simply going to be the addition of the two applied forces from the teachers. So 40 newtons plus, and I'm sure they're pushing in the same direction, this FA2. So that's the net force. That's the left side of the equation I wrote. Now that has to equal the mass times the acceleration of the object. So I'm going to write it again. 40 newtons plus, I don't know what the second applied force is, has to equal the mass of the object, which is 30 kilograms, times the acceleration. And I know what I want the acceleration to be, so I can go ahead and plug that in. Now, this has just become an arithmetic problem. So I can go ahead and simplify this. 2 times 30. We've got 60 kilogram meters per second squared is a newton. So I can subtract that 40 newtons from each side. And I can see that the second teacher has to apply a force of 20 newtons in order to get this object to accelerate at 2 meters per second squared. Okay, that's it for our notes today. Hopefully you understand those. You're going to get some chance to practice it now. Thanks.